So today, we are going to study about solubility, solubility product, and the so-called common ion effect. In the process, I will teach you how to compute for molar solubility, solubility product constant. I will also explain to you how does common ion effect relate to solubility calculations. So let's get started. To start things off, let us define some key terms that will help us understand the topic. Solubility. Solubility is the amount of the compound that dissolves in a specified volume of solution. Solubility is usually expressed as either grams per liter or grams per 100 ml. In equilibria that involve slightly soluble compounds in water, the equilibrium constant is the so-called solubility product constant or KSP. The molar solubility of a compound is the number of moles of the compound that dissolves to give 1 liter of saturated solution. It is expressed in moles per liter. The solubility product expression for a compound is the product of the concentrations of its constituent ions, each raised to the power that corresponds to the number of ions in one formula unit of the compound. This product is constant at constant temperature for a saturated solution of the compound. This statement is the solubility product principle.
To understand KSP, let's take a look at one example. So we are given 1 liter of saturated barium sulfate solution, which contains 0.0025 gram of dissolved barium sulfate. And we are asked to solve for its molar solubility. We are also asked to calculate the solubility product constant for barium sulfate. To solve for the molar solubility of barium sulfate, we would need to convert the given 0.025 gram of dissolved barium sulfate to molarity. To find for its molarity, we will divide 0.0025 grams of barium sulfate to its molar mass, which is 233 grams. By solving this, you will arrive at an answer of 1.1 times 10 raised to negative 5 molarity. That we know the molar solubility of barium sulfate, we can solve for its missing KSP. The dissolution equation shows that each formula unit of barium sulfate that dissolves produces one Ba2 plus ion and one sulfate 2 minus ion. So, per 1.1 times 10 raised to negative 5 moles of barium sulfate would produce 1.1 times 10 raised to negative 5 molarity of barium 2 plus and 1.1 times 10 raised to negative 5 moles of sulfate 2 minus. And as we have done earlier, the KSP expression for barium sulfate would be Ba2 plus times sulfate 2 minus. So, by substituting the concentration of barium 2 plus and sulfate 2 minus, we can solve for the KSP. So, KSP would be 1.1 times 10 raised to negative 5 times 1.1 times 10 raised to negative 5, which would give us an answer of 1.2 2 times 10 raised to negative 10. To solve for part A, we would need to write the proper chemical equation for MgF2. So, MgF2 would dissociate to form Mg2 plus 2F minus. And we would also need to write the KSP for MgF2, which is 6.4 times 10 raised to negative 9. We would also need to write the KSP expression of magnesium fluoride, which is Mg2 plus times F minus squared. We will let S be the concentrations of the ions. So for Mg2 plus, it would be represented by S, and for F minus, it would be represented by 2S squared. So the final KSP expression would be S times 4S squared. And if further simplified, it would be 4S cubed. So to solve for S, we would isolate S and we would end up with that equation of S is equal to cube root of KSP all over 4. And S would be equal to 1.2 times 10 raised to negative 3 m. For part B, we recognize that NaF is a soluble ionic compound that is completely dissociated into its ions. MgF2, on the other hand, is just a slightly soluble compound. Both compounds produce F2 ions, so this is a common ion effect problem. To calculate the molar solubility of MgF2, we would first need to write the correct equation of MgF2. So MgF2 dissociates to form Mg2 plus 2F minus. And again, since we are solving for the molar solubility, we would need to write the KSP expression of MgF2. So KSP is equal to Mg2 plus times F minus squared. And again, we will let S be the missing concentrations of the ions. For Mg2 plus, it would be S, and for F minus, instead of putting 2S squared, we would put 2S plus 0.1 squared. Further simplifying the 2s plus 0.1 squared, we would arrive at KSP is equal to S times 4s squared plus 0.4s plus 0.01. And again, by further simplifying, we would arrive at 4s cubed plus 0.4 squared s squared plus 0.01s minus KSP. Since this is a quadratic equation, we will find for S1, S2, and S3. And S1 would be equal to 6.394836167 times 10 raised to negative 7 m. S2 would be an imaginary number and S3 would also be an imaginary number, so I did not included it in the answer. Compare the two molar solubilities by computing for their ratio. We would just need to divide the molar solubility of MgF2 in pure water all over the molar solubility of MgF2 in NaF. So 1.2 times 10 raised to negative 3 over 6.4 times 10 raised to negative 7 would be equal to 1900 over 1. So that would be the ratio for the molar solubilities of MgF2 in pure water over the molar solubility of MgF2 in NaF.